Okay, so last time we were working on lumped capacitance models, and we had done an analytical solution to a problem and had done a numerical solution using the simplest possible numerical technique, which is Euler's technique. Just to remind you, this, let me get my pen. This was the problem we were working on right here. We had an object that was subjected to this time-varying ambient temperature, which is shown over here, and we wanted its response. So we had calculated a BO number, and we had decided that we could lump all this material together as being at one temperature, and we did an energy balance on that material, and that gave us this state equation. So again, every numerical technique that we look at is going to require a state equation, and the state equation is just this idea that you have to be able to compute the time rate of change of temperature if you're given time and temperature. And for this particular problem, this is the state equation. Okay, so we had done Euler's technique. Euler's technique is this idea that if I want to move through any time step, all I do is take the temperature at the beginning of the time step and the time at the beginning of the time step. I plug it into my state equation to get d temperature, d time, and then I just assume that that's constant throughout the time step. So it just gives me sort of a trajectory that I use to shoot across the time step. Euler's technique is first order. Now we showed that last time. We said that the first order nature of this is evident in the fact that you only have to calculate the state equation one time to move through the time step. So we're only getting the first derivative, and what that ends up meaning is that the global error of our simulation is proportional to the time step to the first power. And it's also explicit, right? If you look at this equation we're using to move through the time step, everything on the right hand side is known. I know at the beginning of the time step the temperature and time, and it's an explicit equation to give me the temperature at the end of the time step. And the practical implication of that is this is going to be unstable. So today we're going to look at several other techniques that are better than this, more advanced, and they'll either be more advanced in that there will be higher order, or they will be implicit, right? So the first sort of method that we'll talk about is a predictor-corrector technique. So predictor-corrector techniques is a whole class of techniques, and the idea behind these techniques is that you take some predictor steps, and those predictor steps are used to basically gain information about what's going on inside of the time step, and these are just Euler steps. They're very simple. And you can take one or many of them depending on how elaborate the technique is, but once you've got done taking these predictor steps and you've gathered information about what's going on inside of this time step, then you put all that information together and you take a corrector step that actually predicts the temperature at the end of the time step. So the simplest possible predictor-corrector technique is Hoyne's method here, and it consists of only taking one predictor step and then the corrector step. So the idea is we're only going to take one predictor step, and that predictor step is given here. It's just an Euler step. So if I'm coming into this time step, my predictor step is, let's calculate the time rate of change here at the beginning of the time step, right? That's what I'm doing right here. And we'll use that to make an estimate of the temperature here at the end of the time step. And the little hat here is important. It means that this is not my final answer. This is just me taking a step to try to gain some information. So at the end of that predictor step, what do I have? I have information about what's happening at the beginning of the time step. I have some estimate of what's happening at the end of the time step. I have to put all that information together in order to calculate the actual temperature at the end of the time step. And the most logical way of doing that is you just calculate the time rate of change at the beginning of the time step using everything you know about that. You calculate the time rate of change at the end of the time step using everything you know about that. And you'll notice there's a squiggle here. And then you take the average of those two time rates of change, so that's why there's a 2 here, and you use that to shoot through the time step, right? So predictor step gives you some information, and then the corrector step is where you put all the information together to actually move through the time step. Still an explicit technique, but higher order. And you know it's higher order because you've calculated the time rate of change not once but twice to move through the time step. So let's look at what that looks like in, I guess, first of all, ease. If I can find my ease program. So here's Hoyne's technique programmed in ease. What I did is what I usually do, which is I first go through the first time step and make sure that works, and only then do I go through all the time steps. So this is me taking my predictor step, right? So I calculate the temperature at the end of the time step, but you'll notice there's a little hat here to indicate that's just an initial guess for what that, or an initial estimate for what that is. And then I calculate the actual temperature at the end of the time step, and I get that by taking the time rate of change at the beginning of the time step, which is this part of it, and then the time rate of change estimated at the end of the time step, and then you divide by 2. So once I make sure that works, I can check the units and everything like that. Then what I'm going to do is comment this out and take this code and put it inside of my duplicate loop and take all the time steps. So that's what I've done right here. The rest of this is my analytical solution, which I'm using just to make sure that I can get the global error. So at this point it should work. If I use, let's see here, 10 time steps, so 11 times is 10 time steps, gives me a time step of 0.04 seconds. My global error is 1 Kelvin, right? So the maximum difference between the analytical solution and the numerical solution anywhere inside of here is 1 Kelvin. If I increase the number of time steps to 100, so 10 times the time step, I should see that the global error goes down by not just 100, not just 10, but 100 times, right? So if we look at this characteristic, at 0.04 seconds I had 1 Kelvin. At 0.004, so 10 times less, I have 0.01 Kelvin, so 100 times smaller global error, right? So that's the outcome of this being a second order technique, is the global error goes like delta t, not to the first power but to the second power. If you think about where that comes from, because I'm estimating the time rate of change twice, I'm basically not only getting the derivative, I'm actually also estimating the second derivative every time I take a step, right? So now my local error is all this stuff out here, right? The biggest one being delta t cubed. So my local error is now proportional to delta t cubed, where this constant is related to the third derivative. My global error is the sum of all these local errors, so that ends up being delta t squared, right? That's my second order technique. And you always win in terms of computational speed by going to these higher order calculations, at least for explicit techniques like this. If I want 0.01 Kelvin accuracy, let's see, I was getting that with 100 time steps, right? Now it's a little more complicated to go through every time step. It requires 2 evaluations of the state equation, right? So for at least this problem, that's 200 calculations. 100 steps times 2 calculations per step is 200 calculations. If I look back at my Euler method, with 100 steps I had 0.7 Kelvin accuracy. And remember, Euler method was first order accurate, which means that I'm going to need then, if I want the same accuracy, 0.01 Kelvin, I'm going to need 70 times as many steps, right? So I have to reduce this down to 0.01. That's going to be 7,000 steps. So each step is only 1 calculation, but still, you know, there's many more calculations required. The Hoyne's technique would be about 35 times faster than Euler's technique for this problem, right? And you know where that ratio sort of comes in at depends a little bit on how expensive it is to calculate your state equation. But this is a very cheap state equation, so it's pretty much linear with calculations. Okay. That's a very simple predictor corrector technique, but already you're seeing a massive improvement in terms of efficiency. That's a little out of the order. So one that's a little more common is this Runge-Kutta fourth order technique. So RK4, if you see RK4, that means Runge-Kutta fourth order. It's just a predictor corrector technique. It's just that there's many more predictor steps so that you get up to fourth order. So in the Runge-Kutta technique, you would take 4 predictor steps and then finally take 1 corrector step. So let's go through the technique over here. You basically just follow this algorithm that I've laid out. The first thing you do is calculate what we're going to call AA. So AA is the time rate of change at the beginning of the time step. So here I'm entering this time step. I know everything about what's happening right here at the beginning of it. I'm going to calculate the temperature d time, and then I'll use that to get t hat at j plus a half. So what is this here? This is the temperature at the beginning of the time step plus dt times delta t over 2. This is an estimate of the temperature halfway through the time step, right? And then I use this temperature here to calculate BB, so that's a new estimate of d temperature d time. I'm using t at t hat j plus a half, and if there's anything that depends on time, I would use the middle of the time step time too. And then what do? I use this estimate to recalculate the temperature at the midway point of the time step, right? So I'm using 2 little squiggles on top of this to indicate that it's different than this one, but it's just TJ plus now BB times delta T over 2. So now I have another estimate here of the temperature at the middle of the time step. Again, I use that to calculate the time rate of change, right? So here I'm using T with 2 squiggles above it to indicate that that's the the estimate of the temperature at the middle of the time step and the time as well. And then finally, I do one more predictor step, which is let's use this time rate of change to calculate the temperature at the end of the time step, right? So now I'm using CC times delta T. I'm going to go all the way to here, right? And finally, then I use that to calculate the time rate of change at the end of the time step. So what is the outcome of all these predictor steps? Well, I have here, if you look at it, one estimate of the time rate of change here at the beginning of the time step, that's AA. I have 2 estimates right in the middle, that's BB and CC. And then I have 1 estimate at the end, that's DD. So I have 4 estimates of the time rate of change inside of this time step. The last thing I need to do is put them all together in a way that gives me the corrector step, right? So I put that all together to give me my actual temperature at the end of the time step. It's going to be the initial temperature, and then you can see all I'm doing here is I'm weighting those 4 estimates of the time rate of change. So 1/6 of what I got at the beginning, plus 1/3 of what I get in the middle, plus 1/3 of the other one in the middle, plus 1/6 of the one I got at the end. That's going to give me my estimate of the actual time rate of change inside of there on average, and then multiplied by delta t. And you just keep doing that for every single time step. This is one that's obviously easier to put into MATLAB than it is into ease, because you can overwrite all these intermediate variables in MATLAB, and at least if you're using the equation window, you can't do that in ease. So let's look at what this looks like in MATLAB. Where is that? Right here. So let's see if I can make this a little bit bigger. I think preferences. Yeah, sorry. Okay, so here's all the initial stuff. Let's take 11 steps. So, sorry, 10 steps. And then this stuff here is just going through each time step, right? So hopefully this information here exactly corresponds to what I put in that previous slide. You can see I'm overwriting AA and T hat and BB and so forth every single time step, and then this is the corrector step. And I just move through time. Even in MATLAB, I can get the analytical solution to get the global error. So let's run this. And where is it? Right here, I guess. What's going on? Okay, so the global error is, what is that, 0.3 millikelvin with just 10 steps, right? If I go to 101 steps, so this is 3 times 10 to the minus 4. This is a 4th order technique, so now I'm going to take 10 times more steps. I should see this global error go down not by 10 or 100, but actually by 10 to the fourth, right? So this should be really, really small. And yeah, it goes down to 2 times 10 to the minus 8. So ridiculously accurate at this point. If you think about it, you really win with a technique like this because, what did I do? I thought I had put this somewhere. I think my slides are out of order. Well, all right, it doesn't matter. If you think about it, you really win with a technique like this because with just 10 steps, I am at, what is it? 0.3 millikelvin, right? So if I wanted the same accuracy of 0.01 Kelvin, I mean, I think I could get by with just like 4 or 5 steps and I'd get that kind of accuracy. Now, again, each step is 4 times as more difficult, right? Here I have to evaluate my state equation 1, 2, 3, 4. So it really depends on how expensive this equation is. But if it's easy like this, this is 4 times 4 is like 16 calculations, right? Versus, what did I need? 200 with Hoyne's technique and 7,000 with Euler's technique. So you can really see the computational gain that you get by going to these higher order techniques. Now, the Runge-Kutta technique is still an explicit technique, right? Doing this in MATLAB was easy because everything was still an assignment. So it will go unstable if I try to take time steps that are too large. And actually that becomes more of an issue with a very accurate technique like this because you might find that I can take large time steps and have good accuracy, but I can't take large time steps because I'm going to go unstable. So that kind of brings us to the next kind of technique, which is implicit techniques.